Okay, so we're in section 6.2 now, and this is using, I'm not sure if we call it separation of variables or not, but let's see, are we calling it, we're just talking about, we don't get to separation of variables to the next section, but we're solving differential equations, kind of like we did before. Okay, so we're going to do number 2 first. So 2 has, here's our differential equation, and because we're not giving any initial conditions, that means that it's going to be a general solution. So we have the derivative, but we're going to set it up as a ratio of 2 differentials. So we multiply both sides by dx. We integrate both sides individually, which we can do. And the right-hand side just becomes the solution. And left-hand side is we have just simple integration. The integral of 4 dx is going to be 4x. The integral of negative x dx is negative x squared over 2, and then we add our arbitrary constant c. So the exponent is 1, so we add 1 to the exponent, divide by the new exponent. And so that is our general solution to problem number 2. And I'm 99.99% sure that I get this right, but I'm just going to double check. 4x minus x squared over 2 equals c. Okay. Problem number 4, section 2. So our differential equation is dy dx is equal to 4 minus y. So we can't just multiply by dx like we did last time, because then we'll end up with y dx. So we need to get the y over to the other side somehow or another. And we can't just, if we subtracted y, then we wouldn't have the y group with the dy. So we actually take this whole thing and divide by 4 minus y. And we'll multiply. So we're going to divide by 4 minus y, and we're going to multiply by dx to both sides of the equation. So what you'll end up with is 1 over 4 minus y times dy is equal to dx. In this case, the simple integration is on the right-hand side instead of on the left-hand side. But we still do that. We integrate 1 over 4 minus y dy is equal to the integral of dx. Well, it's just by itself, just like the integral of dy is y, the integral of dx is x. So in this case, the right-hand side becomes x. It's actually x plus c, but we'll get a constant from both sides, so we can just combine them. So you really don't have to worry about the constant on one side. On the right-hand side, it's just like we did before, except what we would do is we would use u substitution and let the whole denominator be 4 minus y. So du is negative dy, because this derivative of 4 would be 0. The derivative of negative y would be negative 1. So you get negative 1 times dy, or negative dy. Okay, so what we can do is rewrite the left-hand side as, well, before we do that, let's dy is equal to negative du. Same thing, I'm just multiply both sides by negative 1. That way I can substitute directly here. So what I get is negative du divided by u is equal to x. Okay, now we integrate with respect to u, so the integral is negative the natural log of the absolute value of y plus c is equal to x. And it's u, not y. So it's the negative sign, you factor that out. The integral of du over u is the absolute value of the natural log of u. Okay. So now what do we do? Substitute that u back in, which is 4 minus y is equal to, in this case, I'm going to move the constant to the other side. I'm not changing the sign because the constant is arbitrary until I specify initial conditions. So just as long as I have it in there, I can kind of move it around fairly. You know, I could say the new constant is negative the old constant, so it doesn't matter. Okay, now this is the solution, but we might want to actually solve for y instead of x, because x is our independent variable and y is a dependent variable. So we would multiply both sides by -1, so you get natural log of natural log of the absolute value of 4 minus y is equal to negative x, and then again, I'm just going to add c, negative c again. And then to solve for y, what you do is you use properties of exponential functions, logarithms, so you'd have e to the natural log of the absolute value of 4 minus y is equal to e to the negative x plus c. So I use the left and right hand sides as the exponent. And at that point, when you have e to the natural log of something, you just have that something. So you get 4 minus y is equal to e to the negative x plus c. Now, the right-hand side, when you have exponents adding, it's the same as if you had two terms. So it's e to the minus x times e to the c. Okay, now, so what we would have is e to the c is just e to some constant, so this is also just a constant, so we can actually say it's c times e to the minus x. So we do that a lot of times. Instead of having the constant and the exponent, we separate them, because if you multiply two numbers together with the same base, you add the exponents. So you get back to this. This is really just another constant, which we're not going to give it another constant, we're just going to say it's c. Now, as far as the absolute value is concerned, what is the domain of this particular, actually, the range of this thing? I'm just thinking about this. Is there any way to solve for, well, it turns out when you go through this particular step, you can take the absolute value signs off. So this just becomes, so I could really just make this 4 minus y is equal to c e to the minus x. And so if I solve for y, I'll get, this will become -4, but if I multiply it by -1, it'll become +4, and then I get minus c e to the minus x. But again, negative c is the same as c, so we could leave it like that, or we could change it plus c. Again, the arbitrary constant is determined when we have the initial conditions and everything works out well. So anyway, that is the answer. Problem number 7, section 2. Okay, so the differential equation is y prime is equal to square root of x times y. And let's change y prime into dy dx. And even though we're not calling it this particular time, we're going to separate the two sides. So what we could do is we would divide by y and multiply by dx. What that'll leave us is dy over y is equal to the square root of x times dx. So all the y stuff is over here, all the x stuff is over there, so we now integrate both sides. So this, the answer is the integral of dy over y is the natural log of the absolute value of y. And then we integrate that, and this is the same as the integral of x to the 1/2 dx. So to integrate that, we add 1 to the exponent, divide by the new exponent. We add our arbitrary constant, which we could have added to either side, doesn't matter. Okay, so let's we get the natural log of the s value y is equal to 2/3 x to the 3/2 plus c. Now, just like before, if we take, actually when we integrate that, we can, actually when we do this e to the x thing, e to the natural log of the absolute value of y is equal to e to the 2/3 x to the 3/2 plus c. So when this happens, it just becomes y. And here we can break these two things, the sum of the exponents, into two terms. So we get e to the 2/3 x to the 3/2 plus times e to the c. And this becomes just c again, a new arbitrary constant c, but we're just going to call it c because there's no point in doing it again. So that's problem number 7, c e to the 2/3 x to the 3/2. So that's correct. Problem number 17. And 17, find the function y equals f of t passing through the point 0, 10 with the given first derivative. So basically what this is a same as we did before, except we have an initial condition. So number 17 is dy dt is equal to 1/2 t. And the initial condition is that basically f of 0 is equal to 10. So when t equals 0, the function equals 10, not the derivative. So we have to solve for the general equation, the general solution, and then we can apply the initial condition. So we multiply both sides by dt, so we get 1/2 t dt on the right-hand side, and we get dy on the left-hand side. So we integrate both of those since the variables have been separated. So the integral of dy is y. Here we get 1/2 the integral of t dt, so we get 1/2 the integral of t dt, which is t squared over 2, and we add an arbitrary constant c to the whole thing. And so that's the same as y is equal to t squared over 4 plus c. So that is our general solution. Then we apply the initial conditions. So y of 0 is 10. So that means we put 0 in for t, which of course this goes to 0, so we find that c is equal to 10. And therefore the final solution, y of t, is equal to t squared over 4 plus 10. So when t equals 0, y equals 10. Okay, so that's the solution to the differential equation. It also says use a graphing utility to graph the solution. So let me minimize that, open up the graphing program, and I'll share that for you. Okay, so here we are. Here's the graphing program. Let's make it bigger. Enter the equation. So the solution is going to be t squared divided by 4 plus 10. Don't see anything. That's because it's probably out of the bounds. So we're going to zoom out, which means going over here to the left-hand side and using the negative sign. And, oh, I can't use t. I have to use x. Because if I use t, it thinks it's a parametric equation, which we haven't talked about yet. Okay, so there we go. So it's a parabola with a the vertex at 0, 10. And I can move it up and down by going this way. So anyway, that is the solution to the equation number 17. Just make sure I did that right. Yep, okay. Okay, we're problem 19 now. So it's the same kind of deal. Got our differential equation, dy dt is equal to negative 1/2 y. The other one was 1/2 t. So we separate variables. What we're going to do is we're going to divide by y and multiply by dt. And what that will do is we'll get dy divided by y is equal to negative 1/2 dt. Okay, that goes down here, that goes up there. So that's our result. Now we integrate both sides. Integral dy over y is equal to the integral of negative 1/2 dt. So the left-hand side becomes the natural log of the absolute value y. The right-hand side becomes negative 1/2 t plus c. So the integral of dt, you factor out negative 1/2. The integral of dt is t. You add the arbitrary constant. Okay, now we're not going to solve for c yet. We're going to do e to the natural log of the absolute value. Y is equal to e to the minus 1/2 t plus c. Left-hand side just becomes y. The right-hand side is e to the minus 1/2 t times e to the c. But e to the c is a constant in itself, so we get y is equal to c times e to the minus 1/2 t. Now we use the initial condition that at t equals 0, y is equal to 10. So 10 is put on the left-hand side. We have c e to the minus 1/2 times 0. So we get e to the 0. E to the 0 is 1. So you get c times 10. 10 is equal to c times 1, e to the 0. So c is equal to 10. So now we go back, and once we have c, we can then plug it into the general solution. So we get y is equal to 10e to the minus 1/2 t. Okay, so that's our particular solution. This is our general solution. And so let's plot this thing. Okay, so we got 10 exponential minus 0.5 times x. Okay, again, I'm using x because that's just a standard formula. Again, if I use t, then I get something that doesn't look right. So I could put 10 times, so I just put 10 e to the minus 0.5, which is minus 1/2. And we'll graph it, and let's just go to this standard. If you go over here to the left thing, you choose standard. So we're still, let's zoom out a little bit. So it's a negative exponential function. You can see here t equals 0, that y equals 10, and then decays. This is an example of exponential decay, and it goes down to 0 after a certain period of time. Well, it'll approach 0, it will never equal 0. Okay, so problem number 20, what's the next one? 22. This group of exercises that say write and solve the differential equation that models the verbal statement. Evaluate the solution at the specified value of the independent variable. Okay, so 22. So it says the rate of change of n, which is dn dt, is proportional to, well, that means, proportional means that you have some constant of proportionality times the independent variable, which is n. So it's k times n. And we know that at t equals 0, n is equal to 250. And when t is equal to 1, n is equal to 400. What is the value of n when t equals 4? So what we do is we're going to come up with the general, so the question is, what is it? T4, what is n? So the basic procedure is we're going to solve this differential equation. use this to solve for the arbitrary constant. We're going to use this to solve for this constant, the constant proportionality. Then we'll have an equation for n as a function of time. And then we can plug t in and calculate n. Okay, so that's how it works. So the first step is to solve this differential equation. So because I have n on this side, I need to get over there, and I need to get dt on the other side. So we're going to multiply by dt and divide by n. And all these are all exponential growth or decay kind of problems. If k is positive, then it's a growth problem. So we just separated the variables. Two variables, n and t. K is a constant. We don't know what the constant is, but it is a constant. And that's the constant is based on this information. Okay, so we integrate these two sides. Okay, so the integral of dn over n is the natural log of the absolute value of n. The integral k is a constant, so we can bring it outside. Even though it's a variable, I guess it's not really variable. It's a constant represented by a letter. Okay, so we have k times the integral of dt, which is the integral of dt is t. We add our arbitrary constant in this case, which is set by this initial condition. We do e to the natural log of the absolute value. N is equal to e to the kt plus c. The left-hand side just becomes n. So n is a solution. And here we have e to the kt times e to the c. But e to the c is just another arbitrary constant, so we get c e to the kt. So this is our general. It's not even a general solution yet. I guess it is. It's a general solution. Okay. But we have two unknowns. We don't know what c is and we don't know what k is. That's why we have two things specified. So we're going to use the first one to get c. So t equals 0, n equals 250. T equals 0, n equals 250. So plug in t equals 0 onto the right-hand side, and n is 250. Okay, it doesn't matter what k is. 0 times k is 0. 0 times a million is 0. So you get e to the 0, which is 1. So we see that c is equal to 250. So now we have, by applying one of those conditions, we have n is equal to 250 e to the kt. Now we have to use the second condition, which said that when t equals 1, n equals 400, I think that's what it was. Yeah, we use that to find k. Okay, so n is 400. 250 e to k times t, which is 1. So what we're doing, you have to solve for this part before you solve for k. So you get e to the k is equal to 400 divided by 250. So what it is, I moved that over here, I divided both sides by 250. So if I divide 400 by 250, I get this, and if I divide 250 by 250, I get 1, and then I switch the sides. So let's just go ahead and calculate what it is. 400 divided by 250. 400 divided by 250 is 1.6. Okay, so e to the k is equal to 1.6. So how do I solve for k? Well, I take the natural log of both sides. So it's kind of opposite of what we've been doing. Before we said, e to the natural log of something was something. Here, the natural log of e to something is something. So the left-hand side becomes k, and the right-hand side is just the natural log of 1.6, which you use a calculator for. So I get k is equal to 0.470. So our final solution, which has all the constants identified, is n is equal to 250 e to the kt, but k is 0.470 times t. So now we know everything. We can plug t. If we plug t equals 0 in, we get And I just realized I forgot to do e right here. So it's 250e to the 0.470t. If we put t equals 0 in here, we get 250. If we put t equals 1 in here, we'll get 400. And now the question is, what is it when we put 4? What is n of 4? And when t equals 4, we get 250e to the 0.470 times 4. So we do that in our calculator. 250 times e to the x of 0.470 times 4. So just so you know, it's 250 times e to the 0.470 times 4. So that's what you put in your calculator. Push enter, and we get 1640. I rounded it off to 3 significant figures. So that was 22. Let me just check, make sure I did that right. Yeah, they say 8,192 divided by 5. 8,192 divided by 5 is 1640. Okay, so that's it. Our next problem is 25. So 25 is one of this group. We're just going to do one of them. What we're doing is we're given there's an exponential function, y is equal to c e to the kt, just like we solved for in 22. And we're given 2 points on the graph, so what we know is that when t equals 0, y is equal to 1/2 from the first point, 0, 1/2, and the second point says that when t equals 5, y equals 5. So 5, 5 is the second point. And given these 2 points, these 2 conditions, we can find c and k just like we did in the previous problem. So the first thing to do is t equals 0. So at t equals 0, we know that y is 1/2. So we get 1/2 is equal to c e to the k times 0. This is e to the 0, which is 1. So c is equal to 1/2. So our initial equation now gets a little bit more. I'm going to put 0.5 instead of 1/2 e to the kt. So they gave us c. The second part of the problem is to find k, so we use the second part. So y equals 5 when t is equal to 5. So if I put in 5 for t and 5 for y. So if we divide by 0.5, we'll get 5 divided by 0.5 is 10. So we get 10 is equal to e to the 5k, or e to the 5k is equal to 10. We take the natural log of both sides. And the natural log of e to this exponent is just the exponent. So we get 5k is equal to the natural log of 10. And so k is equal to the natural log of 10 divided by 5. And let's just put that in the calculator. Natural log of 10 divided by 5 is 0.460. So that's k. So our final solution is y is equal to 0.5 e to the 0.460t. So that is the solution. This is problem 25. So we get, now the book has, the solution of the book is not exactly that, but it is. So I'm going to show you how this happens. If we left that as a natural log of 10, we get the solutions y is equal to 0.5 e to the natural log of 10 divided by 5 times t. Okay, remember how this works. Okay, now let me remember how this thing. Okay, so I think what we can do is we have e to the 0.5, or y is equal to 0.5 e. Now t divided by 5 is outside this, so we can say it's equal to the natural log of 10 to the t over 5. Okay, so this t over 5, which is outside the natural log, can go in, become the exponent. And now what we can do is either the natural log of something is just that something. So you get y is equal to 0.5 this times 10 to the t over 5. Yep. Or I think the book says 1/2 10 to the t over 5. Okay, so there's two ways of looking at it. Okay, that's it. Okay, we're on 34. Okay, the next couple of problems are just dealing with exponential growth and exponential decay, and we're given enough information to solve for all of the parts of the solution to the equation, and we just given different combinations and we find them. So 34 and 37 to 41 deal with half-lives, which is radioactive decay. So the solution is going to be y is equal to some arbitrary constant e to the minus kt. So it's going to be a negative. K is positive, we'll have, but then k times negative is a negative. So this is exponential decay. In half-life is where where y over c is equal to 1/2. It's the time, so it's the time required for the amount to be half the initial amount. C is the initial amount. So in problem number 34, we have that the half-life is equal to 1,599 years, and we have the initial quantity. Actually, we don't know what the initial quantity. We have the amount after 1,000 years. So when t equals 1,000, we know that y is equal to 1.5 grams. Okay, from these two things, the half-life, which says when y divided by c is equal to 1/2, t is equal to 1,599. So how do we use these two things? Well, what we're going to do is we're going to use this first to find k, and then we can use this to find c, and then once we have the equation, we can plug in and get the rest of the stuff. Okay. So the first thing is to use the half-life. And that says when y over c is equal to 0.5, which is half the original amount, is equal to c e to the minus k times t, which in this case is 1,599 years. Well, actually, sorry, because if I divide this original equation by c, y over c is equal to e to the minus kt. So it's 0.5 is equal to e to the minus kt, and where t is equal to 1,599 years. So we have one unknown k. It's in the exponent, so what we're going to do is we're going to take the natural log of 0.5, and that's equal to the natural log of e to the minus 1,599 times k. So all I'll do is change the order of those two. Well, the natural log of e to some exponent is just the exponent, and this is just the natural log of 0.5. So let me go ahead and put that in. Natural log of 0.5 is negative 0.693. Negative 0.693 is equal to negative 1599 times k. So k is negative 0.693 divided by negative 1599. And so I get k is equal to 0.000433, or it's equal to 4.33 times 10 to the minus 4. So that's k. So I can go back and I could say that the original equation is equal to y is equal to c e to the minus 0.000433 t. Now I need to find c. So I know that at t equals 1,000, y equals 1.5. So I can say 1.5 is equal to c times e to the minus 0.000433 times t, which is 1,000. So I get 1.5 is equal to c e to the, okay, so you get 1,000 times 0.000433. So you get negative 0.433. So all I have to do is solve for c. c is equal to 1.5 divided by e to the minus 0.433, which is the same as 1.5 times e to the positive 0.433, because when it goes from the numerator to the denominator to the numerator, it changes sign. So I can plug that in. 1.5 times e to the 0.433, and I get 2.31. So now the original equation can be fully defined. Y is equal to 2.31 e to the minus 0.000433 t. So that's the equation. Now the two things that we didn't know was what the initial quantity is. Well, C is the initial quantity, so it's 2.31 grams. After 1,000 years, it's 1.5 grams. So it decreases from this to that. It decreases to half of 2.3, which would be 1.15 after 1,599 years. Okay. And then the last part is going to be, what is it at 10,000 years? So we don't have to do anything too special there. We just go here and plug in t equals 10,000. So we get 2.31 e to the minus 0.0000433 times 10,000. And that's just a matter of plugging in the calculator. 2.31 times e to the negative 0.000433 times 10,000, right parenthesis, and I get 0.0304 grams, which should be less. As time goes along, we have less and less of the material when you have exponential decay. So that was problem number 34. Let me just check what it is. C is 2.314, which is the initial quantity. 10,000 years, it's 0.03, which is what I got. Okay, we're going to do another one of these exponential decay problems, 37. So carbon-14 has a half-life. So when T equals 5,715 years, we know that Y over C is equal to 0.5, which is equal to E to the minus K t. And what else do we know in this problem? 37. We're given that when t equals 0, y is equal to 5 grams. Okay, so our differential equation is y is equal to ce to the minus kt. When t equals 0, this goes, we get e to the 0. So we get that, we get 5 grams when t equals 0. So e to the 0 is 1, so just c is 5. So that was easy. That's the easiest one. So now we know our differential equations. Y is equal to 5 times e to the minus kt. And then we use this to find k. We don't actually use this form. We divide it by it. So we could say y is 2.5, or we can just start from there. So let's just do that. So we know that 0.5 is equal to e to the minus k times t, but t is a half-life, 5716. So we take the natural log of both sides. You can see the natural log of a half we use a lot because beneath these half-lives you're going to have 0.5 on the left-hand side. So on the right-hand side, because we're taking the natural log of both sides, both terms on both sides, we get natural log of e to the minus 5716 times k. Well, the natural log of 0.5, you think I remember it, 693. Okay, so this is negative 0.693 is equal to negative 5716 times k. The natural log of e to the some power is just the power. So k is, solving for k, you just take the left-hand side divided by the right-hand side. So negative 0.693 divided by negative 5716. In this case, we're going to do it in scientific notation. So it's going to be 1.21 times 10 to the minus 4. Okay, so now we know everything. The equation governing this particular problem is y is equal to 5e to the negative 1.21 times 10 to the minus 4th times t. We already know when you put t equals 0 in, we're going to get 5. That was already specified in the problem. So all we have to do is plug in t equals 1,000, t equals 10,000. So 1,000 years, well, since we have half after 55,716, we should be somewhere between 5 and 2.5, which is half. It's probably going to be closer to 5 than it is to 2.5. So 5e to the minus 1.21 times 10 to the minus 4th, that's minus k times 1,000. So all this involves just plugging into your calculator. So 5 times e to the negative 1.21 e to the minus 4 times 1,000, close the parenthesis, and we get y at 1,000 is 4.43. So we said it was going to be closer to 5 than it was to 2.5. And then the other case is 10,000, which is on the other side. So this should be somewhere between 0 and 2.5. So again, all we're doing is plugging in the value of t into this equation. So we can actually just recall the previous equation and change 1,000 to 10,000. So insert a 0 in there, and I get 1.49. These are grams. And now we're just going to check the answer. 4.43, 1.49. Done. Number 41, which is also a decay. It's really just a word version of what we have done. So it says radioactive radium has a half-life of 1,599 years. So we know that when T equals 1,599, that Y over C is equal to 0.5. And we know that Y over C is equal to E to the minus KT. Because our solution is Y is equal to C E to the minus KT. So we can, and the percentage is this ratio. So after this is 0.5, the decimal equivalent of 50%. So what we're going to do is we're going to solve for K, and then we're going to plug T in, and then we'll get a ratio, which will be the percentage. So we have half of the remaining when T is equal to 1,599. And as I said, we could go back, since we've already done this, problem 33. When we did that, K was equal to, yeah, they didn't actually, we're going to do it. So the natural log of 0.5 divided by 1,599. So if you solve for K, we've already done it, so we don't need to do it again. K is equal to negative, or actually positive, because I have the negative sign here, is positive 4.33 times 10 to the minus 4. So we know that Y over C is equal to E to the minus 4.33 times 10 to the minus 4 times T. This gives us the decimal equivalent of the percentage. So to get the solution for this, all we have to do is plug in at T equals 100 years. We know that Y over C is equal to E to the minus 0.433 times 10 to the minus 4th. That's minus K times T, which is 100 in this case. And so we get E to the negative 0.433, E to the negative 4 times 100. And so we get 0.9957. And to get the percentage, all you do is multiply by 100. So the percentage equivalent is 99.57%. Wait a second, did something wrong here. What did I do wrong? I don't know. So let me just pause it. It's not a big mistake, but okay, I don't want to put in the calculator wrong, but it would be E to the minus point, oh, it's point, that was my problem right here, it's 4.33. Okay, so if you do that, you get 0.957, which then when you multiply it by 100, you get 95.7%. Okay, so that's it. Okay, now we're going to do some exponential growth problems. And one example of exponential growth is interest. So we have the amount in the account is equal to the original amount, E to the KT, where K is the interest rate and T is the time. And this applies for continuous compounding of interest. So the easiest one is number 43, and it says that P, the initial amount invested, is $1,000. And we know the interest rate. Interest rate is 7% or 6%. which the decimal equivalent is 0.6, which is equal to k. So we know that the amount in the account is equal to 1,000 e to the k times, where k is equal to 0.06. And so that's it. So given that, now we could have put in, t equals 0. This becomes e to the 0, which is 1, and so that's one way we could do p, the principal. Okay, the time to double. What is double? Well, that's when a over p is equal to 2. So all we have to do to answer that question is we say, okay, a over p is 2, and we get e, and that's equal to e to the kt. So k is equal to 0.06 times t. So we just have to solve for t, and we do that by taking the natural log of both sides. Okay, so the natural log of 2 is 0.693. And then we get 0.06 times t on the right-hand side, and you solve for t, and you get 0.693 divided by 0.06, and that's 11.6 years. Okay, the second part is amount after 10 years, and all you have to do there is take the original equation. So if t equals 10, what is a? Well, a is equal to 1,000 times e to the k, which is 0.06 times t, which is 10. So it's just a matter of plugging into your calculator. 1,000 times e to the 0.06 times 10. And just think about this. It took 11 years to double it. So after 10 years, it's not going to be quite double. So double 1,000 would be 2,000. So it's going to be probably 1800 or something like that. So if you don't get that, something's wrong. Okay, so I get 1,822. That's dollars. If it's pounds or euros, the 1,822 euros. It's just a ratio. Okay, so that was problem 43, $1,822. Okay. What's next? Number 43, we did that. 45. Okay, so what do we have? We have that the amount in the account is equal to the principal times e to the kt, where k is the interest rate. In problem number 45, we know that the initial investment, P, is $750. And we know that A over P equals 2 when T is equal to 7.75, 7 3/4 years. So we already know P, so what we have to do is solve for K. So we'll say 2 is equal to e to the K times 7.75. So we take the natural log of both sides. Switch with the constant out front here in the exponent. And the natural log of 2 is 0.693. is equal to 7.75 times k, or k times, yeah, we don't have k. Okay, so we're trying to find the interest rate. So k is equal to 0.693 divided by 7.75. 693 divided by 7.75, 0.89, 0.089, sorry. So that's 894. So That's the decimal equivalent. In terms of percentage, you multiply by 100, so you get 8.94%. So the interest, the annual rate, is 8.94%. Okay, that's great. So then all we have to do to find the amount after 10 years, so at t equals 10, the amount equals question mark. That's what we're trying to find out. So all we have to do is plug into the equation. So the principal is 750. We have e to the k, which is 0.0894 times t. And now we plug in t equals 10, so we get 750 e to the 0.894 times 10. Okay, so 750 times e to the 0.0894 times 10. E is $1,833. And we could put the number of cents we wanted to. 0.67 turns out. This is something we can actually carry out this many decimal places as far as there are cents to put in. Because we start out with $750 even, so it was 750.000 forever. And so we can carry many of these. Okay, up to 47, I think. Yep, 47. Still this exponential growth of a savings account. And we have continuous compounding. And in this case, we are given the initial amount. So we know that P is $500. And we know when T equals 10, that the amount is $1,292.85. Okay, it's probably chosen, so this comes out to be some nice interest rate. So what we can do is we can just A over P, we know that the amount over the principal is equal to E to the KT. So we have the amount, which is 1292.85 divided by the original amount, which is 500. And it has to equal E to the K times T, which in this case is 10. So we're going to solve for K, and then we can, that'll be the interest rate, and then we can figure out how much time it takes to double. Okay, so what is 1292.85? 1292.85 divided by 500. So we get 2.5857 is equal to E to the 10K. Take the natural log of both sides. Natural log of 2.5857 is equal to the natural log of E to the 10K. What is the natural log of the answer? 0.95. 0.95 is equal to 10K. K is equal to 0.95 divided by 10, which is 0.095, or in terms of a percentage, it's 9.5%. So that is the annual rate. So that's the first part of the problem. The second part of the problem is figuring out how long it takes to double. Well, A over P means double means A over P is equal to 2 E to the K, but that's 0.095. We have to use the decimal part, T. Okay, natural log of 2 is equal to the natural log of E to the 0.095 T. Natural log of 2 is 0.693 is equal to 0.095 T. Natural log of 2 is 0.693. I might have said T. So t is equal to 0.693 divided by 0.095. 0.693 divided by 0.095. five, 7.3. So we get 7.3 years to double, where A over P is equal to 2. Okay, so that sounds reasonable. We'll look at the answer. And that was 47. 9.5, 7.3. Okay, it's the last one of the simple exponential decay kind of stuff. So this is problem 63, which is a word problem. And it says the management of a certain factory has found that a worker can produce at most 30 units in a day. The learning curve for the number of units N produced per day after a new employee has worked T days is N is equal to 30 times quantity 1 minus E to the minus KT, E to the KT. After 20 days on the job, a particular worker produces 19 units. Find the learning curve for this worker. How many days should pass before this worker is producing 25 units per day? So all we have to really do is use the information that's given to solve for K, and then we'll have this equation completely defined in terms of the independent variable T and the dependent variable N. So what it says is after 20, when T equals 20, N is equal to 19. And if we plug T is 20 and N is 19 in there, we can solve for K. So we get 19 is equal to 30 times 1 minus E to the K, which we're trying to figure out, times T, which is 20. And what will happen is as T goes to infinity, we get E to the, well actually, is it minus K? Okay. K will end up being a negative number. And so this term will go to 0. E to the minus infinity is 0. So it'll end up being 30 when T equals infinity, which is the maximum number they can do. So they'll learn quickly at first, and then, you know, it's kind of a rate of diminishing returns. Okay, so what do we have? We have 19 is equal to 30 minus 30 e to the 20k. So let's subtract 30 from both sides, and that'll give us negative 11 is equal to negative 30 e to the 20k. Divide both sides by negative 30, so we get e to the 20k is equal to negative 11 divided by negative 30, which is 0.366. Then you take the natural log of both sides. You get natural log of e to the 20k is equal to the natural log of 0.367. I guess I'll round it up. So the left-hand side becomes just 20k, and if you take the natural log of 0.367, you get negative 1. So k is equal to negative 1 divided by 20, which is negative 0.05. So our original equation, based on these two, this one condition, we can figure out what the equation, which is 30, 1 minus e to the minus 0.05 times t. So that's our learning curve. And then for the particular case of where, you know, how many days should pass before this worker is producing 25 units? Well, you know, n equals 25, t equals question mark. So all I have to do is make the left-hand side 25, and you'll have 30 times 1 minus e to the minus 0.05 t. If we multiply that out, we'll get 25 is equal to 30 minus 30 times e to the minus 0.05 t. subtract 30 from both sides, you'll get negative 5 is equal to negative 30 e to the minus 0.05t, or e to the minus 0.05t is equal to negative 5 divided by negative 30. So negative 5 divided by negative 30 is 0.167. Okay, then we take the natural log of both sides. And so we take the natural log of 0.167. And you get 1.18. I did something wrong there. I took e to that number. Something was wrong. Okay, natural log of 0.167. That's equal to negative 1.79. So we get the left-hand side just becomes the exponent. The natural log of e to something is something. Right-hand side is negative 1.7. Ta-da! So t is equal to negative 1.79 divided by negative 0.05 divided by negative 0.05, and we get t is equal to 36 days. So it should make sense that, what was the original thing? To make 19, it took 20 days. So to make 25, it should take more days, which it does, 36 days. So that was problem 63. And we'll just check the answer. 36 days. Okay.